Good morning, and today we're going to look at a different notation for differentiation. We have actually been looking at the Sir Isaac Newton notation, who is a mathematician who developed differential calculus, but at the same time another German mathematician called Gottfried Leibniz also developed differentiation at the same time, and it's really uncertain as to which one of them developed it first, and if one of them developed it and another one stole the idea from it, or if they just completely randomly developed the same notation for differential calculus at the same time. However, we are going to now look at another notation for differentiation. So we've already been looking at the notation f dashed of x, which is the derivative of the function f of x. Now, we know that we can be given equations and functions in the form f of x equals, or we could be given it as y equals. We might be given a quadratic expression as y equals x squared plus 3x, or we could be given that as a function f of x equals x squared plus 3x or whatever. And we know that f of x in this context, f of x and y are exactly the same thing. So if we're given their original function as f of x, then we write the derivative as f dashed of x. But this other notation, dy by dx, is actually the same as f dashed of x. So the derivative can either be written as dy by dx or f dashed of x, and it still represents all the same things as the derivative represented before: the rate of change of the function, or the gradient of the tangent at a point. So if we're given an expression in the form y equals something to begin with, then when we're asked to write the derivative of that function, that expression, we're going to write the derivative as dy by dx. If we're given our original function is f of x equals, then the derivative will be f dashed of x. And if we're given the function as y equals, the derivative will be written as dy by dx. Okay, so here we have something similar to what we've seen before. So the actual differentiation itself is not any different, apart from the fact that we're going to use a different notation. So we know from this type of expression, function, equation, that we are going to have to multiply out the brackets and get everything as a single individual term. So we've done that before. So we're going to have to multiply out the brackets here. We have an x squared minus x minus 6 on the top line. And then we individually make them all over x squared. And then we simplify them. So the first term, x squared divided by x squared, becomes a 1. And then the next one, when you're dividing your x's, you subtract your powers. So that middle term has a top. The top letter there, the x, has an invisible power of 1. So we're really just going to do 1 take away 2, which gives us a negative 1. So that's negative x to the power negative 1. And then the next one, take the x squared up to the top and make it an x to the power negative 2. So we have a negative 6 x to the power negative 2. Now that's us got our y expression already now to differentiate. So we have to now make it clear that we're moving on from having our original function, our original expression to begin with, and we're going to change it now into finding the derivative of it. So we have to make it clear by writing now that we're now doing dy by dx, just as we would have previously written f dashed of x. So we now differentiate. So we differentiate the first term. When we differentiate a constant, the answer of the derivative of that is 0, isn't it? So that constant disappears. So let's now look at the second term. Okay, we multiply by the power, which is a negative times a negative 1, which will be just a positive 1. And we subtract 1 from the power. Negative 1, take away 1 is negative 2. So we have a 1x to the power negative 2, which we just write as x to the power negative 2. And then for the last term, negative 6 times negative 2 is a positive 12. And then subtract 1 from the power is a negative 3. Now, the question was asking you to find the gradient of the tangent to the curve. And again, just to go back to that context, that's a very common differentiation context. When you're trying to find the gradient of the tangent to the curve, you recognise that that's the same as f dashed of x, or in this case now dy by dx, and f dashed of x and dy by dx is actually the same as the gradient when you have an x value to put into that dy by dx or f dashed of x. So we're going to be substituting x equals 2 into this. Now, it's not very easy to work out what 2 to the power negative 2 is, or what 2 to the power negative 3 is. So we do really have to be able to fix these back up into positive powers again to make it easier to substitute the x equals 2 into them. So we're just going to change this one to 1 over x squared and this one to 12 over x cubed. Now remember that 12 does not go on the bottom beside the x cubed. It stays on the top as a whole number 12. Okay, so we are now able to put in x equals 2. So when x equals 2, dy by dx equals, so it's 1 over 2 squared plus 12 over 2 cubed. Now let's just simplify this together. Okay, so that's 1/4, and this will be 12 over 8, which is 1/4, and 6 over 4, which is 7 over 4. But don't leave your answer like that. 7 over 4, is equal to dy by dx, but the question didn't say find dy by dx at x equals 2. The question was given in a context and it asked you to find the gradient of the tangent to the curve, so you have to answer the question and say that you know then that the dy by dx being equal to 7 over 4 simply means that the gradient is 7 over 4, and that's us now answered the question. Okay, now I'm just going to go on a little bit further. That's the question completely finished, but let me just show you what I mean by this. We've worked out that the gradient is 7 over 4. Here is the graph of this function that we've been given. Okay, and what we're saying then is, what is the gradient at that specific point at x equals 2? Now that gradient will be different depending on which x value we're looking at. So we're looking at x equals 2. That's the line that represents the gradient at x equals 2. So we're asking what is the gradient of that line at that specific point. And it would be different if it would say x equals 3 or x equals 4. So you've got to have the x value to get the specific value of the gradient. Okay, and that would be the gradient there. Okay, so next question, we're going to be asked here, differentiate r, which is equal to 16p to the power of a half with respect to x. With respect to p. So we're asked to differentiate r, which is this function here, with respect to p. Now, first of all, when we are making up the notation for the derivative of a function y, which is equal to x's, then we write it as the difference of y over the difference of x, which is the derivative of y over the derivative of x. So dy by dx is how we write that, okay? And this time we're going to write to differentiate r with respect to p. So we are going to write it as dr by dp, the difference of the r's with respect to the difference of the p's. We've got to use the letters that are given in the question. So we have it all ready to differentiate to begin with. So we're going to write it as dr by dp. We're not going to write it as dy by dx because we don't have any y's or any x's. We have r's and p's this time. So we put the letters together that we're given. So this one's going to be dr by dp when we differentiate it. Okay, so we multiply by the power, 16 times a half is 8, and we subtract 1 from the power, so we have 1/2, take away 2/2, which is p to the power negative 1/2. Okay, now we have differentiated it. We're not putting in any numbers, so we could leave it like that. That would be absolutely fine to leave it. But we could also bring it back to be a positive power, and if we want to be really smart, we could make it back into a third as well. Now, if we were to take this p onto the bottom, it would be p to the power positive 1/2. And if we were then to turn it into a third, it would be 8 over the square root of p. Okay, and that's it. That's as much as you can do with that. Okay. Right, so we're now on to exercise 6i. And your page number might be different depending on the edition of your book, but we're on to exercise 6i and we'll look at questions 1 to 5. Okay, as always, ask your teacher if you need any help, and take care and good luck.